This is the Concept Velocity Lab, and my name is Sam Uruji. So the purpose of this lab was to compare the measured position data versus predicted position data of an object moving at a constant velocity to observe the motion. So some of our physics principles in this lab are Newton's first and second laws. First law is object stays in rest or in motion if it is at motion or at rest, and if it is not acted upon by any forces. And Newton's second law slash the momentum principle is an object's acceleration is proportional to force applied or inversely proportional to its mass. Some equations we used were final velocity is initial velocity plus net force over mass times change in time, and then final displacement equals initial displacement plus average velocity times change in time. Assumptions we had were that there's no friction acting upon our object, no air resistance, meaning that the net forces were zero, and then it was on a flat surface. We only care about displacement in the x-axis, and no acceleration, causing a constant velocity. So preview of the lab was that I had a tennis ball moving in a constant direction, constant velocity. I recorded the movement of the ball, uploaded it to Tracker to compute experimental data, and I used time and displacement data to compute predicted data via the computational model in GlowScript, then compare it to the experimental velocity of the ball. The setup was I rolled a tennis ball on a flat surface while filming the whole path of its movement in the shot. And the system was a tennis ball because that's what we were tracking and what we care about its behavior. And the surroundings were the countertop because it causes friction, gravity and normal force from the table act upon the ball, and then the air around the ball, which may cause drag forces. Our initial conditions, which we calculated from the tracker right here, and then the time started at 0 seconds. So with tracker, we uploaded a video of the ball, and then the center of the mass was tracked in each frame with the point mass feature to update the displacement and the change in time. And then that was graphed to give us our velocity, which was a pretty linear line indicating that the ball appears to be moving with a constant velocity. So the computational data with the VPython GlowScript, we inputted our initial conditions like the ball's mass, initial position, initial velocity, and then time equals 0. And then using the code, it gave us this predicted position over time graph, which is a linear velocity. So next we use a Google Sheet to plot the experimental position and the modeled position. The slope of the position over time for the computational model is similar to the experimental data's velocity slope, but slightly larger because we said the net forces on the ball equal to 0, so it did not account for any external forces on the ball in the computational model. The computational model depicts a ball that's actually moving with no constant velocity, and in the experimental one, there's friction and air resistance acting on the ball, so that's why the slope is less. Theoretically, if the ball was moving with constant velocity, the lines would be the same, but that's not the case. And then sources of error were friction, wrong center of masses in the tracker, acceleration from pushing the ball at the very beginning. And then finally, additional questions. So if the orientation of the x-axis was flipped in tracker, then the results would have the same velocity, but the graph would be reflected across the x-axis and just have a negative slope. And then it's not possible to say how many pushes and pulls forces are added to give 0 net force on our model because the model predicted the ball to roll further than it actually did. It did not account for the horizontal forces acting on the ball like friction or air resistance because we said the net force is equal to 0. But we do know that the forces such as gravity and normal force equaled 0 because they cancel each other out. We didn't have any movement in the y direction.